what we're going to try to do today is we'll definitely finish up chapter 7, and then we'll start into chapter 8. When I post this, I'm going to break it up into 2 videos so as not to, for chapter 8 to get lost. But I don't think that we're going to go past really what you already know and get to the point where we start into the X-ray emission spectrum. Okay, so we'll talk again about X-ray production. We'll hammer home again how inefficient it is, and we'll talk about emission from the tube, which is not the same thing as X-ray production. So what we did on Wednesdays, we talked about the anode, and of course we're going to use a rotating anode. One thing that I did miss is the induction motor, of course on the outside of the tube, is stationary. So the rotor rotates, the stators stay stationary. Okay, so the stator is the induction motors on the outside of the X-ray tube. So we talked about, in context of the anode, we talked about focal track, and that's tungsten alloy. And it may, or the entire disc may or may not be made of tungsten. It may be, something else with the tungsten focal track actually embedded into it. So we said we use tungsten because it has a high atomic number, thermal conductivity, high melting point, and I gave you a little bonus that it doesn't warp whenever you heat it up. So that's very important. Not on any test that you're going to find, but for your understanding. So the rest of aside from the focal track, the rest of the anode disc can be pretty much made of anything that withstands a lot of heat, lighter metals, whatever. So some of them will utilize a graphite backing, and the purpose for the graphite backing is to keep the heat in as much as you can from conducting, further down the stem and then causing bearing wear and that sort of thing. So it keeps as much as it can of the heat off of the bearings. And again, if the bearings heat up, then they fuse together and you have a stationary anode. We talked about focal spot being the point of impact, and we rotate the anode. We use a rotating anode to spread that area of impact out so that we also spread out the heat. So we talked about the angle of the bevel is about 15 to 20 degrees, or 5 to 20 degrees, depending on the function of the tube. Our special procedures tubes are probably going to have a more steep, memo tubes are going to have a more steep bevel. That means going closer to 0. Most of them are about 17. Okay, so we talked about bibevel tubes. Those are tubes, again, with special purposes. You're probably not going to work with them. Bifocus tubes, every tube is bifocus. It's important not to confuse those two. Bifocus tube means you've got two filament sizes, so you can use 2 focal spot sizes. But the point of impact is the same on those. A bibevel tube, point of impact somewhere else. So you've got 2 different angulations on your anode. So we talked about the angling of the anode and its role in the line focus principle. With the line focus principle, because of the angulation of the anode, what we have is a relatively large area of impact. That's what we refer to as our actual focal spot. The effective focal spot would be what the patient could see if they were laying on their back and collimator housing was gone and really the protective housing was gone. And the patient could see that angulation. It's how big it would look like to the patient. So in using that high angulation, 5 degrees, whatever, we're going to get more sharpness for recorded detail. So 2 things affect sharpness for recorded detail in the X-ray tube: size of the filament and the angulation of the anode. So we talked about the anode Hill effect, and that's the difference in intensity between the cathode and anode end of the X-ray tube. It's lower on the anode end of the X-ray tube, and that is because of the filtration effects of the anode. Some of those photons that are made have to penetrate through the anode to get out of that end, and therefore we're going to have a higher amount of inherent filtration on the anode end of the X-ray tube than on the cathode end of the X-ray tube. Intensity decreases. So one thing that I missed was off-focus radiation. So off-focus radiation is radiation that's created anywhere aside from on the focal track. So, if we're looking at the profile of the anode, we've got these electrons coming across the tube and they're moving, right? So they're moving at, you know, again, maybe upwards of half the speed of light, and they're little bitty pieces of matter, essentially. They're so small we don't give them a number, but they're little bitty pieces of matter. So you throw something hard enough at something, what's it gonna do, potentially? Well, it'll break, yeah. We'll get to break here in a bit. What bounce, they're gonna bounce, right? So what we've got then is a positive charge, a negative charge, and that's what causes all that acceleration. So we've got a high velocity electron, and it might hit this solid target, and it might have a tendency to want to bounce back that way. But what is the charge of the electron? It's negative, so while it's trying to go that way, we know what about like charges? Yeah, they're going to push back this way. What do we know about unlike charges? They're going to pull, right? So it's getting pushed from that direction, and it's getting pulled from this direction, and it's going to go back. And if it hits right back on the focal track, you're golden, right? But if it hits right here, and it bounces, and it reaccelerates, and it hits there and creates an X-ray photon, that's an X-ray photon that's created off of the focal track. And what do we call that? Off-focus radiation. Okay, so what does off-focus radiation do? Well, just kind of reverse engineering that. How do we get, what do we use to get the best resolution out of our X-ray tube? We angle the anode, but what else? Large or small focal spot? Small. Right. So when we use small focal spot, we get a smaller area of impact on the target. Right? Stand to reason. Well, if now we're making them up here, what did that do? Yeah, it kind of increases the size of the focal spot. So what's that going to do to sharpness of recorded detail? It's going to decrease it, right? So okay, this is getting a little bit ahead. Into next semester, we're going to talk about blooming of the space charge and what all that does, and we've talked about it a little bit, right? So you know what that is. You stand on the rotor too long, you use a really high MA station, you're going to get some blooming, and what you're going to have a tendency to do is to equate blooming with off-focus radiation, which you are 100% right to do, you know, because our focal spot is our intended area of impact, right? So, you know, in a perfect world, it wouldn't be any bigger than the filament. But if we get such a large space charge that those electrons can spread out more once they get past the focusing cup, because they're all negative charges, and our point of impact is here, you know, all the way across from here down to there. What do we have? By definition, all the photons that are created between here and here are off-focus radiation. But we're not going to call it that. We're going to call it the enlargement of the focal spot due to the blooming of the space charge. Is it off-focus radiation? 100%. You're going to get a whole lot more of that than what you are that, you know, those few that bounce. So what's this going to do to sharpness of recorded detail? Decrease it. It decreases it because you've got a larger point of impact. Effectively, what you're doing in this case is maybe that's small filament, but you made the large filament out of it, right? So that's part of the reason, along with the creation of the heat, that we don't want to rotor up for a long period of time. It creates blooming and space charge and reduces sharpness of recorded detail. All right, so off-focus radiation, bouncing electrons, blooming of the space charge, enlarges focal spot size, both decrease sharpness of recorded detail. All right, any questions on what we did last week or that? All right. Then what we're going to talk about is the causes of failure, which we've talked about all semester long, and we've talked about on Wednesday as well. almost everything's going to be attributable to heat, right? So long exposure times, high MA stations, rotor in a long time, all of those things take their toll on the X-ray tube. But the X-ray tube is going to fail eventually anyway because of heat. We create heat, we send heat across the tube, it impacts, so we deposit the heat. As you know, the anode, because of the friction of the electrons trying to go back into the system, might generate its own heat. So we got heat, we deposit heat, and then we got to do something with it. So we got three ways that we deal with the heat. One is thermal radiation out to the envelope, right? So it radiates out to the envelope, and then surrounding the envelope, you got that oil, and then it conducts it into the oil. And then, you know, if your tube is designed such, you may have some sort of fan, and again, it might not be an active fan, but it's going to blow air across, you know, at least it may not actually blow air off of the oil, but it will work kind of like a radiator in your car, right? So air goes through what the oil goes through, and therefore it removes some of the heat. So what we've got is conduction. You know, we got conduction moving all over the anode, or at least all over the disk. We've got thermal radiation, we've got convection. So all three of those help us to cool the tube down. It's still going to fail. So what's going to cause it to fail? One of a number of things. Rough handling can cause tube failure. But in the context of heat, what we're going to be dealing with is, yeah, bless you, is, okay, so what did we talk about on Wednesday? What happens as the tube ages? The light bulb analogy. Tanning, exactly. So you got tanning. All right, so you've got a specific amount, and it's really, in context of filtration, it's not as significant as what it used to be. Okay, so you have a specific amount of filtration that you have to legally make an X-ray on a patient. And, you know, at least human. I don't know if veterinarians have different or not, but it's 2.5 millimeters of aluminum equivalent. And there's a lot wrapped up in that equivalent. So it doesn't necessarily have to be aluminum. It's got to be something that absorbs X-rays, and if it absorbs enough X-rays to get us to how much 2.5 millimeters of aluminum would absorb, we're golden, okay? So what provides that inherent filtration? Well, what's the first thing the X-ray beam hits?
Oil.
Another oil.
Envelope.
Envelope, right. So envelope, you know, and let's say this is a glass envelope. If we lay down a layer, well, the glass is going to absorb some X-rays because nothing is radioapparent. It's radiolucent, so it's going to absorb some of the X-rays, but if we put a layer of metal down on top of it, it's going to, in a word, absorb more, right? So it increases inherent filtration. Inherent filtration, or any kind of filtration, used to really affect the imaging quality of the X-ray beam. Not so much anymore. It used to be that the more filtration we put into the imaging system, the less contrast we'd have, the more gray the image would look. And we're going to talk about inherent filtration and added filtration and that the effects on the emitted X-ray beam on Wednesday when we get back. All right, so it increases inherent filtration. We got a layer of tanning. The layer of tanning itself is not necessarily the cause of the failure. It used to be, if you lost the imaging characteristics of the X-ray beam, you know, you just had to replace your X-ray tube. But it doesn't affect contrast that much anymore. What affects your contrast now is your computer algorithm. So you got a digital image that brings out the contrast. That tanning is probably not really going to affect your imaging enough for you to notice. Okay, but what comes with the tanning? Arcing, exactly. So that then is two things, both of which are caused by, you know, heat, and, you know, in one case we've got the buildup of hot electrons, and then we've got the tanning. So we've got, you know, hot electrons jump into a surface that was created by hot electrons. right? So we kind of have a compounding issue. Most common cause, for instance, tube failure, tanning. So we have tanning. Tanning increases inherent filtration, right? So that's all I'm saying about filtration today. So we have tanning. So we also talked about, I don't know where I'm putting my markers. The stem. So what does the stem have to rotate on? Bearings, exactly. And if they get too hot, they get all scrunched up together. They don't rotate, right? And then you got a stationary anode. With stationary anode, what you can have is a pitting, all right? So tanning, we'll say bearings, bearing wear. And that's going to give us, grinding sound to start. Eventually stationary anode. And then pitting. Okay. So what else? What else might happen to it? What else might cause the stationary anode? And think about that. What might cause stationary anode? Give me a hint. What might cause the stationary anode not to even try to rotate?
The stem might get damaged by heat too much.
Well, that's your
that
bearing wear. What about induction motor failure? That might not actually be caused by heat. That might be a cause of tube failure because you've got a stationary anode, but it might not be caused by heat. So that would be an example of something that heat didn't cause. But back to heat, what else might we have? We're getting into winter time, right? So let's say you wake up on a frosty morning and you got a little bit of time, but you don't want to wait too long, right? You don't want to crank your car and wait for the defroster to, melt it all. You go inside and you boil some water and throw it on your window, right? No, why? It's shattered. Okay, so same thing is going to happen here. If your first exposure of the day is at tube limit, potentially you can put all those hot electrons on a very cold anode, and metal gets cold, right? I mean, even if it's in a room at room temperature, you put your arm on it, it's cold, right? So cold anode, hot electrons, crack the anode, okay? So some of your tubes and your manufacturers will, finish my thought up here, high heat load, cold anode. So some of your manufacturers require a warm-up procedure to try to get your tube warm to make sure that doesn't happen. So some manufacturers, GE used to have this. You'd walk into a room, you'd try to take a chest x-ray or something like that, and it wouldn't allow you to make an exposure. You had to go through the warm-up procedure. So it was a series of x-rays. As relatively low KVP, relatively low overall mass, and it might be 10 x-rays just to heat up the anode before you can make an exposure. Ironically though, that warm-up procedure created more heat than what the chest x-ray ever would have, so you don't see it quite as much as what you used to. Okay, so what else?
Filament burnout.
There we go. Open filament. Open filament. All right, so eventually you're going to burn your x-ray tube out, right? So open filaments, the last one. All right, so you have a couple of different charts that I want to bring your attention to. Neither one of these are on the test. Neither one of these are on the final. And I'm not sure, I don't think that they're on the registry anymore. You might look through the content specifications, before you take your registry, but I don't think either one of them are on the registry. So you got radiographic rating charts on page 125, and in the radiographic rating charts, what they do is they tell you what kind of exposure you can make, and it still be an exposure safe for the X-ray tube. Okay? So you see the lines, you see where you got KVP on the left-hand side, you've got the lines that represent your MA, and on your horizontal axis at the bottom, you've got time. So you can calculate, exactly what your KVP and your MA and your time would be to make a safe exposure, single one-time exposure. So what you'll notice in that is, you got 4 charts down there. One, the 2 that are on the left-hand side are 3,400, and the 2 on as RPMs. The 2 on the right-hand side are, CT tube or special procedures tube rotated at 10,000. And what you see between those, just at a glance, is you've got more lines on the one that rotates at 10,000, right? You got more lines because you have more options in this particular diagram on your MA station, but you've also got a whole lot more heating capacity because of that rotation of 10,000 RPMs. So that's your rating chart, and if you flip over to page 127, you'll see anode cooling chart. So you've got, your one chart shows you maximum exposure that you can make, and it'd be safe for the X-ray tube because of the heat that you're going to put on the anode and create on the cathode. And the other one is telling us how long it's going to take to cool the X-ray tube down whenever it gets up to heat. All right, so again, neither one of those are on the final. I just want you to know what they are. Just in case I'm wrong on the registry, you can kind of recognize these things. But what is on the test are, and as far as I know, they're still in the content specifications, is calculation of heat units. But calculation of heat units is really pretty simple. So heat units for a single phase machine is just KVP times MA times time. That's it. Keep it in mind that, this further confuses the matter, but keep it in mind with a 3-phase machine, what we get, if we shoot perfect X-ray on a single phase machine, how much more do we get on 3-phase? It's a factor of 2, right? Instead of 3, it's a factor of 2. So you would think that you would create twice as much heat on 3-phase, right? But no. If you look at the calculation of heat units for 3-phase machine, is KVP times MA times time times 1.4. Okay, so it's 40% increase in heat, 100% increase in output. You make it work.
Is it because of the 14% loss that you?
Well, that's I don't know if there's a correlation there or not, but that's a good connection. Yeah, that's a good connection. 14%. Yeah, maybe you cracked the code. I've never cared to dig into it and see why it is that it's not higher than that. But so anyway, so that's chapter 7. Any questions on chapter 7 before we press into chapter 8?